Now, the last class, I finished talking about temperature scales. And specifically, what you need to know is that you have to, the only way to know these is to memorize it. And that is, we observed that ice melts or water freezes, depending on how you look at it, always at the same temperature. This is 32 degrees Fahrenheit or 100 degrees Celsius, which is the metric temperature scale. Likewise, water boils at sea level at 212 degrees Fahrenheit or, I'm sorry, this should be 0 degrees C, thinking backwards here, or 0 degrees C, 212 Fahrenheit or 100 degrees C. That looks better. So at sea level, water boils, and this is true whether you boil the heck out of it or whether you just simmer it, or regardless of what you do, significant amount of bubbles occur at 212 Fahrenheit or 100 degrees centigrade, and water melts or ice melts at 30 degrees Fahrenheit or 0 degrees C. And this is absolutely universal. It doesn't depend on how much ice you have or how much water you have, and because of this, we use these as the standards of temperature. I mentioned that a thermometer is just some substance that expands, and you stick it in a mixture of ice and water. Wherever it goes to, you label that this way. You stick it in boiling water at sea level, and you put a mark on it and label it this way. As you go up above sea level, the temperature at which it boils goes down. And so as a result of this, when you cook using boiling water at altitude, it's not too bad here, but if you went to Denver, Colorado, where the altitude is 5,000 or 6,000 feet, you'll discover that things are undercooked if you boil them, because the water boils at a lower temperature. So this is the basis for our temperature scales. Now, this also indicates a strange property about heat, and an important property. If we take a sample of ice, say from the Arctic, where it can get down to 40 degrees below zero, really, really cold, and we add heat to that, I'm going to make a graph, and on this graph, on the horizontal axis, is the heat that we add to the substance. And over here, we'll do this as degrees C, and for the heck of it, we'll start here at about negative 40. There are places on the earth where it can get colder than that. It's hard to believe how cold that is. We never normally experience anything like that, okay, thank God, all right? Well, if you start with, and what we got here is 1 little cube of ice, a gram of water. That's a little under ½ an inch square, okay, a cube, a little less than a cubic centimeter on the side. We dig that up in the Antarctic, or the Arctic where it's really cold. We keep it insulated so that it stays cold, or refrigerated, whatever. And then we start to add heat to it. Now, you know what happens normally when you add heat to a substance. It gets warmer. And indeed, our little cube of ice gets warmer. So this is ice. solid. Add heat to the ice, it gets warmer. But then something remarkable happens. When it reaches 0 degrees C, we discover that it starts to melt. And as I just said, a mixture of ice and water in equilibrium is at 0 degrees. What happens is you add heat to it, but the temperature does not go up. Instead, the ice changes from a solid into a liquid. You add heat to it. You can take a bowl of ice, stick it in a pan, start heating the pan. You got to keep the pan stirred now, okay? You can stick it on a red hot burner, and as long as you keep that stirred, and as long as you have a mixture of ice and water, the temperature will be 0 degrees C. You are adding heat to the substance, but its temperature is not changing. When you add heat to a substance, the temperature may not go up. It may stay the same. And this is called a phase change. Here we have ice and water mixed together. When the ice melts, that is called a phase change. And as we add the heat to it, the heat causes the ice to turn into water, but it doesn't increase the temperature. And there's a word for this. Iso means constant. Isothermal means constant temperature. You don't say temperature is conserved because it's not a physical quantity. It's constant temperature. The melting of ice is an isothermal process. Now this doesn't mean the heat doesn't do anything, it does. It changes it from a solid into a liquid. But while this happens, the temperature stays the same, which is quite remarkable. Now of course this doesn't stay forever. Eventually all of the ice turns into water. And the moment that all the ice becomes water, when you add heat to the water, well, of course, like your water heater, the temperature goes up. So here we have ice and water, or we have solid, we have ice and water, we have solid and liquid. Here we have liquid. And so now we have water, and of course, as you add heat to the water, the temperature goes up. But then a remarkable thing occurs. When you finally get up to 100 degrees C, something remarkable occurs. The temperature no longer goes up. The result, you get steam. Once the water reaches 100 degrees C, suddenly we again have an isothermal process. And this process continues for a very long time. What we get now is water and steam, or water vapor. So as you add heat to the substance, once again, the temperature of the substance does not go up. But something does happen. It changes from a liquid to a gas. All right? And this goes on for quite a while. You have to add a tremendous amount of heat to that little gram of water to turn it all into water vapor, to evaporate it, to vaporize it. And then finally, after you've done that, so this is abbreviated here, we have to continue on. Eventually, you wind up with only steam, and then there's no limit to how warm or hot you can get the steam. So I want you to notice something. it takes heat to turn a solid into a liquid. And the amount of heat that you must add to turn 1 gram of ice into 1 gram of water, all at 0 degrees, is called the latent heat of fusion. The heat to melt 1 gram of ice at 0 degrees C is the latent heat of fusion. Fusion is the proper word for melting. It takes heat to turn a substance from a solid into a liquid. First you have to get it up to the melting point, and then you have to add this latent heat. Latent means unseen. You don't see this because the temperature doesn't go up. You see it because you change from a solid to a liquid, but it's latent because it doesn't show up as a rise in temperature. Any questions there? It's weird. Now, once you get up to here, we now have the same thing taking place, that once we get the water up to the boiling point, the extra heat we have to add, the heat to vaporize 1 gram of water into water vapor or steam is let's see, the heat to vaporize 1 gram of water at, it's got to be all the way up to the, first you have to get it up to the boiling point. The heat to vaporize 1 gram of water at 100 degrees C is called the latent heat of vaporization. It is called latent because as you add the heat to it, you'll notice this. If you take a quart saucepan, boil it, get it up to boiling on the stove, you have to boil it forever to boil it away. And if you stick a thermometer in that boiling water, whether you vigorously boil it or whether you just barely simmer it, that thermometer will hold steady at 212 degrees Fahrenheit or 100 degrees C. This is called a change of phase. The latent heats are associated with a change of phase. The phase of a substance is whether it is a solid or a liquid or a gas. So the heat to take it from the solid to the liquid phase is the latent heat of fusion. The heat to take it from the liquid to the gas phase is the heat of vaporization. Now this has incredible consequences in our everyday lives. If you play around in the kitchen, does anybody know of how you should properly melt chocolate? Yeah, you don't watch the cooking channel like my wife does. She has I might as well strip off all other 1,499 channels and just wire it, hardwire it for the cooking channel. Okay, not really, but if you watch that, they'll tell you that if you're working with fine chocolate and you get it too hot, it separates and you ruin it. And good, really good chocolate is expensive. So what you do is you use something called a double boiler. And a double boiler utilizes this process. All it takes is your heat source on the stove. You have a pan of water in that. Here's your heat. And then you have another pan inside that, and this is where you put the chocolate. And no matter how hard you boil that water, as long as it's above a simmer, this will not go over 100 degrees C or 212 degrees Fahrenheit. It's an automatic temperature regulator. Now, if you run the double boiler at very high altitude, you're going to find that it won't heat as much, that the temperature at which the water boils will be less, and so you may have to take longer to melt it. But anytime you want an automatically regulated temperature without any electronics or any fancy stuff, you simply use this natural behavior of water to regulate the temperature. Other consequences of this. If you've ever been around a teapot and you've got the water boiling in the teapot, you can touch the side of the teapot briefly, very briefly. You can touch the teapot very briefly, and if you measure it with the temperature or with the thermometer, it'll show 100 degrees. 100 degrees. You put a thermometer in the water in the teapot, it will show 100 degrees. You stick the thermometer outside of the teapot spout, and the thermometer will show 100 degrees. The water in the teapot, the steam coming out of the teapot, the side of the teapot are all at the same temperature. You can quickly touch the side of the teapot. You might even quickly touch, if you've got a pan of water, you might quickly touch the water. Don't stick your hand in it, right? But just do it like that. Anybody ever stick their hand near the steam coming out of a teapot? Yeah, so what happens? It hurts like hell. Yet, a thermometer shows that the temperature of the steam coming out is the same as anything else. So why does the steam burn you so much more, even though it's at the same temperature as the water or the side of the teapot? The answer is right here. If you run this backwards, if you have water vapor and you wish to turn it into water, you must take out the heat that went into it. So steam at the same temperature as water contains more heat because it contains that latent heat of vaporization. And when that steam touches your hand, it condenses and turns back into water, and it gives up that latent heat, and that is what makes it burn so bad. This is why steam burns are very bad, because the steam contains extra latent heat. A lot of extra latent heat. And so does water vapor. So we will also see something else. So this is something that can be very useful, so take careful notes of this. If you run an air conditioner, we run an air conditioner in one of our bedrooms in the summer. I can stand the cold weather in the winter. I don't like it, but I can stand it. I hate the dog days of summer. I hate that. I can't handle that. I like to work hard, but I don't like to sweat. Okay? Now, when we turn off the air conditioning for the day, what a lot of people will do if they have a bedroom that they've air conditioned is they turn off the air conditioning on those doggy days of summer. Then they open up the windows and they open up the side window and the front window, and they have a big fan blowing all the air in from outside. And then at night they close the windows and turn on the air conditioner, and if you watch a thermometer in the room, you will discover that the temperature in the room doesn't go down. At least not right away. Not right away. You see, the air conditioner is not working. It might feel cooler, but the temperature won't go down. The reason is, it is taking the moisture that's in the room and condensing it back into water, and it's trickling out onto the roof or out of the window. That's why air conditioners drip, because they pull the humidity out of the air. They take the latent heat out. They remove all of this latent heat. They have to get rid of that. And that turns the vapor back into water. And then once it starts to get dry enough in the room, then you'll start to see the actual temperature start to go down. It'll still feel cooler because the fan will help, and also because the humidity is going down. That makes the water in your sweat evaporate faster, and so you feel cooler. But the rule here is this: if you have a room that you sleep in, that you air condition at night, that you air condition at night, during the day, keep the windows closed and keep the door closed so that the humidity outside doesn't get back into the room. Then at night, when you go up, quickly get in and close the door, turn on the air conditioning. It doesn't have to pull out all of that latent heat, and you'll find that it will cool down much faster. This is also true if you have a room in the house. Don't open it up during the day unless you're going to be in it. If you're not going to be in it, keep it closed up and keep that humidity out. Another thing you'll see where you'll see this is that if you have a dehumidifier, I have a dehumidifier in my basement, and during the summer the basement gets fairly warm. Now we'll see there's two reasons for that. One, the dehumidifier draws electricity, which is energy, and it's going to turn it into heat. So all the electricity coming out of the electrical outlet for the dehumidifier goes out into the room. But also, the latent heat, the unseen heat in the form of moisture in the room, is pulled out, causing the water vapor to turn into water and be collected by the dehumidifier. But that heat, which was not sensible, that's why it's latent, suddenly becomes sensible heat. The heat coming out of the dehumidifier is larger than the electrical equivalent. So you're taking all of that latent heat stored in the room, you're turning it back into the room and turning it into what we call sensible heat, and you're also drying the room. Question or yeah?
Yes.
Really loud for the camera. Okay.
What does sensible really mean?
Sensible means I can sense it. Sensible means it's heat that you can detect with a thermometer. Latent means the opposite of latent heat. How's that? Latent heat is, we're going to see, it's energy that cannot be sensed by the thermometer. And so a dehumidifier takes the latent heat in the room, turns it into sensible heat. This is how it's spelled. So if it's not latent, how's this? Then it is sensible. All right? All right? How does your body cool itself? Partly by your body is warmer than the air, and so you have a temperature difference and heat flows from your body out into the air. But when that doesn't happen fast enough, your body produces water. It puts water on you. The water evaporates. It takes the sensible heat from your body. It turns it into latent heat by evaporating, and it cools you. So sweat is your body's way of using the concept of latent heat to cool your body. You'll also notice this in the deep of winter. You take a shower, and when you step out of the shower, most of the time you freeze your patushka off. It's like, oh, you know, oh God, oh, you know. Now for some of you that might feel great, but for me it's like, oh. The moment you dry your body, take that towel, and the moment you get that water off of your body, because when that water is evaporating, it's absorbing heat from your body, and it's becoming latent heat. See? So these things have important ramifications. And a final thing. We've seen this happen, I think, 3 times already this year. And that is hurricanes and thunderstorms. Now, we didn't seem to have a bad thunderstorm season here, but certainly the hurricane season has begun. We've already had 2, 3 hurricanes, tropical storms, whatever. I think they now just group them all and say tropical cyclones. But what happens in the tropics is that water evaporates from the oceans all summer. We're going to talk about the heat in the water as well as the heat in the water vapor. Okay? Water vapor builds up. Water vapor represents stored latent energy. Now, we haven't proved that heat's energy yet, but we will. But let's just say that. And so if the atmosphere becomes unstable, the vapor can rise, turn back into water. It rains, of course. But that latent energy becomes kinetic energy in the form of, what do you call kinetic energy in a hurricane or a tropical storm? I heard it. The wind. And what happens to a tropical system as soon as it goes over land? Boom! It starts to peter out. There's still plenty of water there, but as long as it has a source of water vapor, it has a source of energy, and that's what happened here with this last one. It just sat on the shore, sucking in moisture from the tropics, turning it into kinetic energy, dumping it as rain and blowing everything all over the place. As soon as they start to move inland, they start to wind down. Yet they can go hundreds or 1,000 miles and still have plenty of energy to wreak havoc. They can dump so much water that they can flood everything out. So it is the latent heat in water vapor that feeds thunderstorms and feeds tropical cyclones. So water vapor is a potent source of energy, as we will see. Any questions here? Now, if you continue to study heat, which is what we're doing, we're studying heat and its properties. You discover something remarkable. One of the things you can do is you can take water, because water is everywhere. Water, 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 water everywhere. And you can say, if I have, let's go back to that little cube of water, 1 gram of water. And it's not at the boiling point, okay? It's at the temperature you and I can be comfortable with. If you add a certain amount of heat to that, what you get is that little cube of water (1 degree centigrade warmer. And the amount of heat that will do that is a calorie. If you have exactly 1 gram of water, that's a centimeter. You look at your ruler and look at the centimeter there, a little under ½ an inch on a side. If you add 1 calorie of heat to that, what you'll do is you raise its temperature exactly 1 degree Celsius. Okay? Provided it's not at the boiling point. Provided it's not at the boiling point. And not in a mixture of ice and water. Then things will look different. Okay? By the way, a food calorie is actually 1,000 calories. And does anybody know what snack food I think has more calories than any other snack food? I love these things. Anybody know? Little Debbie's. You get one of these Little Debbie cakes, and there's something like 440 calories in it. That's actually 440,000 of these calories. Once when I was a kid, my mom would buy these little oatmeal pies. You ever had those little oatmeal pies? I ate, as a kid, the entire box of like 8 oatmeal pies in one sitting. She was so mad at me. I said, well, you don't have to put them on my lunch now. Okay? I love them. But it's pure calories, okay? What is interesting is, if you do this same experiment with other substances besides water, you discover that the amount of heat needed to raise the temperature 1 degree C is different. In particular, if you take a piece of steel, 1 gram, a gram of steel, and you say, how much do I have to add, how much heat do I have to add to get 1 gram of steel 1 degree C warmer? It's amazing. It's only about 1/11th, I think, or 1/9 of a calorie, okay? I think it's 1/9 of a calorie. It doesn't take much energy at all to heat up or cool down steel. Very, very small. In other words, it's 9 times easier to heat up and cool down steel as it is water. Aluminum, which is very common, it's about 1/5 or 1/4. Most metals are much easier to heat up and cool down than water. And the amount of heat that it takes to heat up 1 gram of the substance, these are all called the specific heat. It's the heat needed to raise the temperature of 1 gram of the substance 1 degree C. The specific heat of water is 1 calorie per gram per degree centigrade. The specific heat of aluminum is approximately 1/4 or 1/5 of a calorie per gram of aluminum per degree centigrade of temperature rise. And this also goes backwards. If you say, what do I need to pull out of the steel to cool it down? 1 degree C is about 1/9 of a calorie per gram per degree C. Some things are easier to heat up and cool down than others. You want to see this one at work? Take an empty quart pan, aluminum saucepan, and put it on a heated burner on the stove. Now be careful. And you'll notice that it heats up and cools down right away. Right away. You put the smallest amount of water inside the bottom of that pan, and suddenly it becomes much, much harder to heat up, because that water is now also absorbing heat. Metals have the lowest specific heats. Water has one of the highest. Again, this has important consequences. The shortest day of the year is around Christmas in the solstice, which normally would mean it should be the coldest day of the year. But the coldest part of the winter occurs more or less around late January. And the sun is up highest and up longest around June 21st. Yet the dog days of summer come about a month later, after the 21st of July and in August. How come of the delay? Why the delay? It's because all of the water on this planet is absorbing the heat in the summer. A lot of the sunlight bringing heat in is absorbed by the lakes and the streams and the ocean. And so it's cooler than it should be, because the ocean, the water in the ocean, is absorbing lots of heat. By the same token, when we get to the winter, the lakes and oceans give up that stored energy, give up that stored heat, and make it warmer in the winter than it would normally be. Who can tell me what climate has the biggest temperature extremes between the night, the deep of the night, and the heat of the day? The desert. Why? There's no water. So you go down to Death Valley, you think of Death Valley as being horrendously hot. Yep. But you spend the night there and it's horrendously cold at night in Death Valley. There's no water to release and absorb the heat, and so you get these temperature extremes. See? So the amount of heat that something contains doesn't just depend on the temperature. It is true that the warmer it gets, the more heat it holds. But if I ask you this, now let me ask you this. If I have a block of ice, say 100 grams of ice, or let's say 100 grams, of ice, just ready to melt. It's just ready to melt. And then I have 100 grams of water, also at 0 degrees C. Do they contain the same amount of heat, because you've got the same substance, the same amount, the same temperature, or does one of them contain more heat? And if so, which one? Aiden?
The water has more heat.
The water has more heat, because think about it. What must you do to the ice to turn it into water? It's already at the melting point. You must add the latent heat of fusion to get it to turn into the water. So this contains more heat, a lot more. Likewise, if I have the water at 100 degrees C, and then I have a container blocked off, closed off, with 100 grams of steam at 100 degrees C. So I've got to keep it, enclosed so it doesn't go all over the place. Also at 100 degrees C, it's still the same substance. They're at the same temperature and we have the same amount. Do they contain the same amount of heat? No. This contains much more heat. Think about what you have to do to this water to turn it into the steam. You've got to boil the living daylights out of it to turn it into it. So the amount of heat that something contains depends on how much of it there is. Let's just finish that. Heat content depends on the mass. How much mass is there? Obviously, more mass, everything being the same, means more heat. It depends on the substance. Is it aluminum? Is it water? Is it, steel? What is it? It also depends on the phase. Is it a solid, liquid, or a gas? And it also depends on the temperature. So let's stop right there, and we'll pick it up on Wednesday. Okay, bye-bye.
Oh, there's no quiz?
There will be a quiz on Wednesday.